Today, class, we're going to continue talking about gravity a little bit. And to do so, we're going to do a couple example problems on a guy who's on the Earth and then goes to the space station just to see how his weight may change. And if you don't remember, weight is just the force due to gravity acting on the two objects. Okay? So first of all, we're given a couple things. Know the mass of the Earth is 6 times 10 to the 24th kilograms, and its average radius is 6.4 times 10 to the 6 meters. So first part, we're going to use the formula for gravity and find the force of gravity on a 90 kilogram man standing on Earth's surface. Now, if you remember, when you're using the equation, which is the force due to gravity equals big G, the big constant, mass of the Earth times mass of the man divided by the distance between them, and it's squared. Now this is careful, this is distance from the center of the Earth, not from the surface. So if we want to find this for our guy on the surface, well, G is just 6.67 times 10 to the negative 11th newtons meters squared over kilograms squared, times the mass of the Earth, which we were given is 6 times 10 to the 24th, times the mass of the dude, which is just 90 kilograms, so almost nothing compares, divided by the distance between them. In this case, we just need to deal with the radius of the Earth, which is 6.4 times 10 to the 6th meters, and we square that because it is an inverse square law. So we do that, we plug in some numbers, and we see that the force due to gravity on the dude while he's standing on Earth is 879.3 newtons. Most of that obviously is because of the mass of the Earth, not the mass of him. Now in the second part, using the same formula, he is now 400,000 meters above the Earth's surface on the International Space Station, and we want to know what his weight is there, how it compares to 879.3 newtons. So we're going to do the same thing. We are going to use the same equation. The force due to gravity is just G, mass of the Earth, plus mass of the man, again, distance between them. So, but in this case, you gotta know the distance is the radius of the Earth plus that 400,000 meters. So that's where the difference comes in, is we have that little bit extra there on our distance between them. So if we get a gravitational force, same big G, so 7 times 10 to the negative 11th, Newton meters squared over kilograms squared. The mass of the Earth hasn't changed, as far as I know. It is still 6 times 10 to the 24th. Mass of the guy is still 90 kilograms. And now we have to divide it by, well, we'll just put both of them together. Radius of the Earth is 6.4 times 10 to the 6 meters. Plus 400,000 more meters. And then you have to be careful, make sure you square the outside. This actually becomes 6.8 times 10 to the 6th. If you notice, 1, 2, 3, 4, 5, 6 puts it there, so it's actually 6.8. And again, we can plug that in to our calculator. It gives us a new weight of 778.9 newtons. So that's his weight on the International Space Station. If you compare that to the 879.3, it's about 100 newtons less, but he's farther away, so it makes more sense.